So, thank you very much for inviting me along. Looking forward to this evening. I hope you like the catchy title, but how do you queue? And it was, I don't know whether you've been involved in many queues today. I had a pretty good day today. I didn't have to queue for my breakfast. I didn't have to queue on the cycle track to work this morning, so that was okay. But later on in the day, as we're coming up here, I think we had quite an experience of a number of queues. We were queuing at traffic lights, we were queuing at roundabouts, we were queuing at roadworks, we were queuing where the road narrows. All these different things were queues along the way. So it is the sort of thing that interests me, and you know, that's the aim, is to talk about those sorts of things this evening. As Rebecca said, we are obviously from Lancaster University. I'm part of the management school there, but a particular part that links quite well into the statistics part of it. And the particular link that we've got goes under this heading of story. The ST is just statistics. OR stands for operational research. I don't know whether any of you come across that. It's sort of mathematical modelling applied to sort of business problems, that sort of thing. And the I think is for industry, although I did wonder when you said impact, but I think it's for industry. So it is a joint venture between the two departments, and particularly looking at the use, the application of these sort of things in industry in general terms. Okay. So queuing people sometimes think as being a British thing. So perhaps just think about that in one or two ways to start with. A quote from quite a long while ago now, an Englishman, even if he's alone, forms an orderly queue of one, is an impression anyway that people have of us. Other perhaps impressions or other things that point in the same sort of direction, a cartoon there, sports that the British excel at. Queuing is apparently one of them. Just a picture of a queue, I think associated with wartime, but clearly everybody taking it very patiently and so on. It's just part of life. That's actually a queue. Do you know where it is a queue from? The colouring of that would give it away if the colouring was better. It's sort of Wimbledon green, that. Okay, so this is people queuing in a very orderly sort of fashion, hoping eventually to get into Wimbledon. That's a very orderly queue of, I think, British Airways aircraft, and a very orderly queue, in a sense, of fire engines. So the fire engines, I'll talk about the fire service a little bit later on. I'm wondering here whether it is the fire engines that are queuing. Okay. So how does the rest of the world behave in the same sort of situations? Well, what do we think? I went to Singapore 12 months or so ago. That is queuing in the Singapore underground. So, you know, I think that person at the front of the queue has got there by size and elbows rather than by any other means. And it is such that they press it so hard that when the doors open and people need to get out, they're not going to be able to get out because of the people trying to get in. So that's a rather disorderly queue. I thought that was quite a nice picture of another disorderly queue, in a sense. They are all people waiting to cross this section of road, and it really looks as though that person has taken a bit of a flyer. So, you know, perhaps those are the impressions we have of other parts of the world. But just to perhaps balance things out a little bit, that clearly is a very orderly queue, and it clearly isn't, well, it clearly is in China. And that one really caught my eye. I don't know whether you can see that clearly enough. There's two service points here. People are all here sat around in quite comfortable seats, and their places in the queue are being reserved by their shoes. So I thought that was quite a nice sort of example. And it's not just people or the human race that are queuing. That I think you could describe as a queuing situation, waiting for the bird feeder there. So I don't think it is fair to say that other people don't queue as well. Perhaps we've got a bit of reputation in queuing, but it clearly happens worldwide. Okay, so what have we brought to queuing? Did we bring the word queuing? How do you spell queuing? Who thinks that's the correct spelling? Yeah, you're right. Who thinks that's the correct spelling? You're right as well. They're both correct spellings. And I used to go under the impression that this was the British way of spelling and that this was the American, and they just lazily dropped out one of the letters and so on. But that's not true either. But I favour this one. Why do you think I favour this one? Do you know of any other word that has got 5 vowels in a row? I don't. So I go for that one. And, you know, quite a number of other people use that one. So that's the sort of area we're in. This is supposed to be a statistician's view on it. Am I a statistician? One of the very early workers in this area was a Dane called Agne Krarup Erlang. And I'm confident about his surname, Erlang. Okay. And he was described as a mathematician, statistician, engineer. And it's quite, I think that's quite a meaningful and generally understandable combination of things, really. You know, obviously, a mathematician we know about, a statistician we know, and then we also have quite a good understanding of what an engineer does in terms of trying to make practical use of these sort of things. I started off straightforwardly as a mathematician. I studied pure maths at university and then looked around for a way of trying to apply this maths in various sorts of industries. My particular interest was more in the public sector than in the private sector, but you know, essentially it can be used in both sort of areas. But I, for instance, wasn't interested in going into something like finance and so on. What I found at that stage was a course that was half statistics and half this operational research, okay, which is, well, in fact, it was a subject that first came together really during the Second World War, when they applied all sorts of scientific methods to operations, you know, military sorts of operations. And it got the name operational research, and it certainly included and a very important part of it was the application of maths in that sort of area. So that's sort of what I am, half a statistician really, and within our management school and the particular department which includes this sort of thing is what's called management science. Okay. So how does a statistician actually look at a queuing system? If I said a queuing system to a statistician, what would be the important components of it that would make sense to them? In a way, it's a misnomer. The first thing that's important is that there is some sort of service on offer, and that there are one or more servers who have to provide this service. There are customers of some sort. They may be people, but they don't have to be people who are in need of this service. And if they're lucky, they just get it. But if they're unlucky, they might well end up in a queue. But in fact, you know, there are some queuing systems around that are so well designed, people don't have to queue. And that's good, obviously. But you don't have to have a queue in a queuing system. Okay. But if you think about those components, then there really is a very long list of situations that can be described in these sort of ways. So call centres, numerous queues at airports, various ones to do with transport, fire and police sort of services, where we hope, particularly if they are, you know, fires, for instance, that we've not got queues for them, but they have the components of that, or all sorts of sort of retail outlets. And even if we just focus on one particular area, and as one of my interests is health services, then if you think about healthcare examples, That is a partial list of healthcare examples. One of the first pieces of work I was involved in was actually looking at hospital waiting lists as an example of a queuing system. But obviously doctors, clinics, accidents and emergency, they all have very obvious queues in there. There are some systems down here where you're hoping that they are so well designed that you don't have to queue. Okay? But it's got they are nevertheless queuing systems. Okay. So, if that's what we think of as a queuing system, if we just think of a doctor's waiting room, why is it actually a statistical topic? You know, we can understand it's a queue. What makes it statistical? Well, for instance, if we had a very simple system where everybody needed exactly 5 minutes with a doctor, we could just give patients appointments every 5 minutes, and that would be super and efficient. The doctor would be busy all the time, no patients would have to wait, we would have no congestion, okay? But in practice, that isn't going to happen. What are the things that are going to spoil that? Sorry, okay, this 5 minutes might take 6 minutes or might take 15 minutes, and immediately you've got the next two patients having to wait 5 minutes, 10 minutes for their appointment. Okay, so we get in variability in there. So there is going to be variation in the time that someone needs to spend with the doctor. And what do we mean? We mean that if we were to measure the time that people spent in the doctor and drew it up as a histogram or whatever, we get some impression of the probabilities. So, you know, the average time with the doctor is about 5 minutes, but it really is quite variable. Okay. And also, even if you give people 5 appointments every 5 minutes, they don't necessarily arrive every 5 minutes, so we've got an extra source of variability there. So we can already see that it's going to behave statistically rather than just very, very smoothly and deterministically in that sort of way. Okay. So if that's the area in, let me just tell you about one or two bits of queuing theory. They are, in fact, simple results that Erlang produced early on, and they actually give you really quite an important feel for the subject that helps you understand many different sorts of queuing systems. So, the basic system he looked at was a system in which people did arrive at a certain rate per hour or per minute. And because it's maths, then we've got a Greek letter to represent that, a letter alpha. So the arrival rate is, you know, 5 per minute or whatever. But they do vary stochastically, and suppose that's the sort of distribution of time between arrivals. So it's quite likely that arrivals are close together. You know, quite often the gap between them is only 2 or 3 minutes, but occasionally the gap's as big as 15 or 20 minutes. So that sort of variability. What about the service times? We've got the same sort of idea in mind. Service times vary, same sort of distribution, but whereas that is a rate of alpha per minute, this is at a different rate, sigma per minute per server. Okay. And let's, just for this first example, assume there's just one server. Okay. So it looks like a bit of maths, really, a bit of statistics. I've laid out the conditions, and I'm now going to say, on the basis of these, assuming these things are true, what are the consequences? Okay. So the consequences are, and I'm just reminding you what the letters mean. The number of customers in the system won't just settle down to a fixed number. It's obviously going to vary, and we say it varies stochastically, just probabilistically. Okay. If alpha's less than sigma, so to put that into words, if the arrival rate is less than the rate at which the server can work, okay, the server can process people, then this stochastic behavior will settle down if we wait long enough. Okay, so there might be some starting conditions. Obviously, if our system started empty, then for the first few minutes it's going to tend to be still empty. It's affected by the fact it started empty. But after a while, it will settle down and the early conditions will have worn off, and you'll see what's called the long-term stochastic behavior. Okay. For example, for this scenario here, if people were coming at a rate of 9 per hour, the server could actually treat 12 per hour, so the server can cope, then this little bit of theory would say the distribution of the number in the system, so this is the number of customers in the system, and it includes anybody in service. So obviously none in the system means it's completely empty. 1 in the system means there's 1 there, and because there's 1 server, they're being served. 2 in the system means there's 1 of them in service and 1 of them in the queue, and so on. Okay. And what's more, Erlang showed a very simple formula. In this case, it turns out that the average of this is 3. Okay? But it obviously varies about it quite dramatically. So that's if alpha's less than sigma. What if alpha's bigger than sigma? What if the arrival rate is bigger than the rate at which the server can deal with people? It would? That this would be the other way around. That's almost right, except that it would sort of just keep growing. Okay, in fact, it wouldn't actually settle down to anything. Okay, I mean, if it were to settle, if you put an upper limit on what was allowed in the system, it really would just be exactly the other way around. But if we don't put an upper limit on the number in the system, it actually just keeps growing. Okay, so the queue will keep growing. How fast will it grow? Well, it'll grow on average by whatever the excess of alpha is over sigma per hour, but it will do it stochastically, so it'll have random variation in it as well. Okay, so that was one of his early results. And what's more, there were formula for these things that I've just drawn up. So if the arrival rate is alpha and the service rate is sigma, the average number of customers in the system is worked out very easily. It's just the ratio of those two things. The average number in the queue, again, can be worked out from a simple formula. And the average number of customers in the system altogether, which is in fact obviously those in service plus those in the queue. So if you wanted to do the maths and add those two things together, you'd find it gave you this one here. Okay. So the graphs I was drawing on the previous slide all came basically from these simple equations. And another thing that we note that is really very important, that all these equations, they do depend on alpha and they do depend on the sigma, but they only ever depend on them as a ratio. Okay? So if we had a system in which the arrival rate was 3 an hour and the service rate was 4 an hour, this would be the behavior. If we had an arrival rate a system where the arrival rate was 30 an hour and the service rate was 40 an hour, alpha over sigma would still be 3/4. And so it would behave in exactly the same way, stochastically. Okay. So that clearly is very important, and it is called, and is given a name, and that is called the traffic intensity. So, I mean, it's a comparison, isn't it, of how fast people are arriving compared to how fast the system could deal with them. And that is a very important concept that underpins a lot of queuing stuff. Okay. So if we just think about a one-server system, and for different traffic intensities, I work out the average number in the system, it looks like that. So as the traffic intensity gets bigger and bigger, the congestion gets bigger and bigger at faster and faster rates. Okay, so increasing the traffic intensity from 0.2 to 0.4 is nowhere near as bad as increasing it from 0.6 to 0.8. As you get close to 1, it just takes off. Okay. And so, you know, for any particular traffic intensity, we can read off it the expected number, and associated with each of those expected numbers would be a distribution of number in the system for the different traffic intensities. So one of these results then is the idea that congestion grows with traffic intensity. Now, if you remember, this was just sort of a mathematical result. It was based on these three assumptions, which are often quite restrictive sort of assumptions. So really, it's only been shown to be true if those assumptions are perfectly true. But then lots of other people, subsequent to Erlang's early work, have investigated all sorts of other similar sorts of systems where they don't make quite as strong assumptions, and they still find that this rule holds good, and this sort of dramatic increase also holds good in lots and lots of other queuing systems. Okay. So, if we went back to the idea of a doctor's clinic, and we said that clinic looks rather congested, people are waiting a long while in that clinic, they've got big queues there, how could this idea of traffic intensity help us? What does it mean we would need to do or could think of doing? How would you change the traffic intensity in a doctor's clinic? Sorry, you would? Okay, so if you have less people coming to the clinic, you can therefore space them out further so that the arrival rate per minute or whatever is reduced. Okay, so the alpha gets smaller, the sigma stays as what it was, and you will get the benefits that we're talking about. Okay, and that probably is the big thing that they can do. What else might they try and do? Okay, they could reduce the appointment times, and maybe you've observed your doctor reducing their appointment times as well. So that's another measure which should obviously have the same sort of benefit. Okay, so that's using that sort of idea. Okay. What about this business of variability? It's a slightly finer point, but here we're looking at this original result from Erlang and the graph and the fact that when the traffic intensity is 0.85, on average, the queue in this case is about 5. Now variability, the main variability, I guess, well, the two sources of variability are that they're not all 5-minute appointments, some are shorter, some are longer, and the gaps between people arriving are not always 5 minutes. What do you think would be the impact of reducing, say, the variability in people's service times, consultation times? Do you think it'd make the congestion better or worse? Okay, if it has some knock-on effects, and that's what you're sort of speculating about, then that is quite possible. If you actually were able to control the appointment lengths and say you can have up to 5 minutes but no more than 5 minutes, so to speak, rather than some people get 2 or 3 minutes and other people get 7 or 8 minutes, even though the average is the same, you would find that with lower variability you actually get lower congestion. Okay? And if you increase the variability, even if you keep the average the same, so the traffic intensity doesn't change, you actually get more congestion. Okay. So to implement that in our doctor's clinic, we'd be trying to standardize things, really. And I mean, that comes back to giving everybody exactly 5 minutes. And if you really need more time with the doctor, you're going to have another 5-minute appointment at another time rather than on this occasion. Okay. So that again is another way of trying to control the behavior of a queuing system and reduce the congestion by, if you can, reducing the variability that's in there. Okay. Now obviously one other way in which we can try and improve things is just to have more servers. Okay. What do I actually mean by that? Well, if we just added another server and just think through the logic of that, then actually you could see it as just dividing the total amount of work between the two people. So they end up with half as much to do each. So for each of them, the traffic intensity is halved. And we know what the consequence of that's going to be. We're going to get a dramatic drop in congestion. But in a way, that's fairly obvious. And as a measure, we've doubled the cost. you know, we've had to have 2 doctors instead of 1 doctor. So we achieve benefits, but at really quite a cost. What about something slightly different? We do double the servers, but we also double the arrival rate. Okay? So it's the, you know, per person, they're going to have to do the same amount of work. It's like saying, rather than having that doctor doing their surgery and this doctor doing their surgery, they'll both handle all the patients. Okay? So we sort of, what you'd call scaling up the operation. What happens in that sort of case? You get quite dramatic economies of scale. So for instance, if we thought of, again, a traffic intensity, which is some measure of how busy the doctor's going to be. You know, when the traffic intensity was 75%, it meant the doctor was going to be busy 3/4 of the time, and the other quarter, they had nothing to do. So here I've drawn a line at 90% traffic intensity, using some more formulae that Erlang developed. You can see that if there is just a 1-server system, then on average, the number of people in the queue per server is 8. Okay, so you've got basically 8 people in front of you for the server that you're sort of aiming at. If it was a 2-server system, the mean number in the queue per server drops dramatically to 4. And as we go up through the number of servers, you continue to get benefits, although obviously the benefits aren't as dramatically big. So you do get really quite dramatic benefits just from economies of scale of saying if we work with twice the volume and put twice the resources in, we actually can perform a lot better. Okay. So economies of scale also can reduce congestion. So if we could persuade 2 doctors to actually group all the patients together and give everybody appointments in which they were just told they'd see one of the 2 doctors, we would expect to get quite a bit better performance. Okay. Okay. So these are essentially principles that were first outlined by Erlang, and then other people demonstrated that actually carried over to lots of other more practical situations, and the particular ones that Erlang identified really underpin a lot of what's done in terms of either people managing or failing to manage real queues that are out there. Okay. So let me talk a little bit then about some work that we're a little bit involved in, and others and we've got ongoing work in these sort of areas, and others are also working in the same sort of area. What about the ambulance service as a queuing system? Okay. And I'm particularly picking out the fact that as well as there being an emergency ambulance service, there is also an ambulance service to ferry people to hospital appointments and so on and so forth, which is more of a booked sort of system. And whereas you would hope that with an emergency ambulance service that someone was reached with no delay, because it's very important to get there as soon as possible, with the booked ambulance system, then you can afford a little bit of leeway in terms of exactly when you pick people up. So it's the emergency part of the system that we're interested in. Well, if you think about how we would wish an emergency ambulance service to work, we would hope, one way or another, that it was organised so that actually there was never a queue. You know, if we're one of these emergencies, we really do not want to have to be in a queue waiting for an ambulance. So how have they actually managed to achieve that? Okay. Well, they can't really do much about the variability. Okay? That, you know, emergencies happen when emergencies happen. We can't schedule those in any sensible way. And the time it takes to get there and so on, at least in terms of variability, just depends on the location of the accident and so on. So there's not much at all that can be done in terms of controlling the variability. One of the things they do is to try and scale up as far as possible. Okay? So that, for instance, in Lancaster, they do not have a Lancaster ambulance service because it's a small-sized operation. And if they combine it with the Morecambe ambulance service, it's scaled up, more ambulances deal with more work, and they get the benefits of the economies of scale. Okay. The work that we're actually starting to do is with the North West ambulance service that actually covers the whole of the North West. Okay, so I mean it goes down into Cheshire, includes all of Lancashire, and comes up into Cumbria. I'm not sure to what extent it deals with the north end of Cumbria, but it's up here in Cumbria as well. And they're doing it on that sort of scale, in a sense, to take as much advantage as possible of that. Okay. Now that does throw up other sorts of issues and other sorts of interesting issues, which I'll get to in a second. Let me just mention, in addition to this, then the other idea is, what can we do to reduce the traffic intensity? Okay. What might that mean in terms of the ambulance service? Oh, sorry, I have slipped in here that if there's only one server, the traffic intensity is the arrival rate compared to the service rate at which that one server can work. Okay. The same thing carried over to a system where there's more than one server, in particular S servers, is obviously to compare the arrival rate with the combined rate at which all the servers can work. So that's why we just talk, that is now the expression for traffic intensity. So what could they do in an ambulance system to try and reduce that traffic intensity? Can they change the alpha? Not really, unless you can discourage people from ringing the ambulance when they shouldn't do. Okay, and that does happen, so that occasionally there are from time to time attempts to do that. The S is a matter of putting more ambulances available, and in fact, I guess if you think about it, there are big peaks and troughs in the demand for ambulance service. You know, some times of the day it's very quiet, other times of the day it's much, much busier. So the alpha is actually varying fairly systematically over the day. To keep the traffic intensity sensible, there's not much you can do in terms of how long it takes an ambulance to go to a call and take the person to hospital, but there's quite a lot you can do in terms of the number of ambulances. Okay. Now, obviously, they need enough ambulances for the peak times of day. You know, you'd be silly not to have enough vehicles, but they don't actually have to have all the vehicles available. So, in fact, what they would aim to do is have a staffing schedule so that at different times of the day, there are different numbers of ambulances on the road, and they essentially keep the traffic intensity as low as possible throughout the day. Okay. Extra features of this is that, I mean, I've been talking so far about the size of the queue. They actually have performance targets. For the ambulance service, the performance targets are in terms of how quickly an ambulance gets to the scene. Okay, so they'll set a target that we would like ambulances to get there, and I think it's currently 8 minutes is what they'd like an ambulance to get to if it's a red call, if it's a sort of life and death situation. But they know it's stochastic. Okay, so the target is not every emergency is reached in 8 minutes. It's a proportion, 90% of them are reached in 8 minutes. Okay, so that's the sort of target that they work to. Okay. Now, as you start to think about it, what affects how long it takes for an ambulance to deal with an emergency? And part of that is well, in fact, a large part of it is the travelling time. So, in fact, one of the extra features of this is, okay, we've got, 20 ambulances in South Cumbria. Where should we put them? Should we put them all in the ambulance station? That'd be nice and neat. and the staff would be able to use the cafeteria, the facilities at the ambulance station. But some of the calls would be a long way from the ambulance station. You'd better to have them perhaps strategically placed around the county. So there is an issue of ambulance location, and then there's the question of, okay, you've got the ambulances spread out around the county, which one are you going to send? Well, we would hope they'd send basically the nearest. Okay, but what if there's an equal choice or a near equal choice? There's one here and it's the last one in that bit of the county, and there's one here and there's another 2 or 3 in that bit of the county. Okay, it then becomes a strategic thing to say, well, actually, we're probably better to leave that one up there and take one of these and use that. So it becomes quite an interesting modelling problem where there's a lot of statistical variation to understand, plus these location problems, plus strategies, tactics for, okay, that's got 2, that's got 1 ambulance, but on the other hand, there's hardly anybody lives there, and there's there's a dangerous place with a lot of people living there. So again, there's quite a lot to try and balance in that sort of way. Okay. And if you do then send an ambulance, do you then just leave the other ambulances where they are, or do you relocate them to actually then give better coverage? Okay. There's a fire service example of the same sort, but let me just flick through this one. I mean, in some ways it's like the ambulance service. We don't want any house fires or whatever to have to queue. So we do have the same sort of things in mind. But in fact, I don't know what if you can imagine how often you see an ambulance and imagine how often you see a fire engine, I mean, which do you think you see more of? The ambulances, okay. But I mean, they're trying to do more or less the same sort of thing, but there's a lot more ambulance calls than there are calls for fires, and therefore therefore the scaling up sort of operation becomes a very different one. So you can't use the same sort of solutions, or at least not to the same extent as you use with the ambulance service. So in fact, I mean, I've deliberately selected this picture versus this picture. Here we're seeing the ambulances out on the road, which is usually where you'll see them. Here you see the fire tenders at the station, which is usually where you see them. And it's all because of this different balance in things. So the solution that they end up with is that they really need to have very low traffic intensities. They can't really scale up as much. They need to have very low traffic intensities, which means that most of the time the vehicles are idle. Okay? So the fire service then have a lot of other responsibilities other than attending fires. So, the fire service spends a lot of its time training. The fire service spends a lot of its time doing preventive work, because that's all work that can be interrupted. It's as if it's not there when an emergency comes along. So that they're building that sort of flexibility to have a reduced traffic intensity for their emergency work. Okay. So the last example I've got in mind is, again, some work that we've been doing an area we've been doing a bit of work in, and where we're going to continue to do work, and that is accidents and emergency departments. And you'll have been hearing really quite a lot about this on the news these days. So in terms of a queuing system, they clearly are a queuing system, but they're rather different from the one I drew to start with, in that they are now a network of queues. That often in an accident emergency department, someone will need to come in and see the doctor. As a result of that, maybe they need some tests, or maybe they need to be treated by a nurse. And as a result of these two things, maybe they need to see the doctor again. So it becomes a network of services, and between each of them, you will get people queuing. Okay. And another important feature of it, I mentioned it with the ambulance service, and is also true of this, the arrival rates vary dramatically. with the time of day. So this is a 7-day week, 168 hours, and we see for two types of work: ambulance work, the red work, and blue, the people who walk in, they get themselves there one way or another rather than the ambulance service. Dramatic time of day effects. Early hours of the morning, much lower workload than the middle of the day, especially for sort of walking type of work. And that is Monday, Tuesday, Wednesday. So this is Mondays, and it clearly is visually busier than other days of the week. This is real data from one of the departments we've been working with. We've looked at a number of other departments, and often Monday is basically picks up knock-on effects from the weekend. Okay. So we have modelled this, or we've got some models of this sort of thing. They are quite complicated, and I mean that's just to give you a feel for the sort of complications. This is a diagram based on a Department of Health model of accident emergency, so that they have represented it in terms of saying that even though before they arrive you don't know what sort of patients are coming in, at the end of the day you do know that some of the patients are admitted and they end up taking a set of routes. Some patients are relatively major and they take up one set of routes, and then other patients are less major and they take another set of routes, including being assessed, including being treated, including having tests done, and often including, well, for some of the patients at least, having to wait to be admitted. So lots of queues along the way. Okay. So how do A&E departments perform? Well, that's actually data from a real hospital, which will remain anonymous, where here we're seeing the length of stay, LOS, just how long someone stays in the accident department, measured in hours. Would anyone can anyone describe what's going on with that quite unusual distribution? Okay, which is, do you know what it is? 4 hours. So the government requires that A&E departments get 95% of their patients, because they're not going for 100% because they know it's stochastic, 95% through in 4 hours. And that's how they do it. And I mean, I'm sure there is a little bit of misrecording that edges people from 4 hours and 5 minutes to 3 hours and 55 minutes. But they do put a massive effort into that. They now monitor people's time in accident emergency, and as you enter your your last hour of 4, there's all sorts of signs against your name in terms of they're hoping you're going to get through within this last hour. Okay. But they don't always succeed, as you can see there. Now this is, well, perhaps a little bit too complicated as a graph. We've got 7 lines here for 7 days of the week. And this is, for 7 days of the week. And this is for each day giving you the 24-hour day. And this is counting the number of breaches. So a breach is when someone stays in more than 4 hours. Okay. So it is over a 2-year period. So we are seeing a hospital here with hundreds of breaches per hour, but at least it's added up over 2 years. So anything obvious about what the problem is at this hospital? Mondays. Yeah. They've not really geared themselves up properly for these Mondays. Okay. And I mean, if you exclude the Monday problem, then you can see that they're having more during the daytime than during the early hours of the morning. But in fact, there are many more patients going through during the day than during the night. So that variability isn't as bad. Okay. So basically, what is it they're getting wrong? And what we think they're mainly getting wrong is the staffing levels, which is how they can control the traffic intensity. Okay, they can't do anything about the arrival patterns really. They can't do anything about how long it takes to treat a patient. The patients need what they need, but they can do something about the staffing levels. So, what would a rule be? Well, should the staffing levels follow the arrival rates? That's our sort of traffic intensity idea, that if the arrival rate doubles, let's double the staff, and that would be about the right thing to do. Well, that's the arrival rates, that's the staffing levels that they've got in the hospital for different days of the week. So it doesn't peak when the arrivals peak, it peaks a bit later. And if you pick out Monday and all that, it's just one of the lines, when really Monday is clearly higher up there. So they're not, recognising Monday as the problem day. Okay. But because it's a network of queues, if you just respond to the arrival rate with all your staff, then in fact, okay, whoever sees the patients when they arrive, their staffing levels should follow the arrival rate. But if people then, it ends up being another 20 minutes before they see the nurse staffing level shouldn't respond to the arrival rate, it should respond to this 20-minute delay in some sort of way. Okay. So maybe they should be following the total number of patients in the department. So that's graphs showing how many patients there are in the department. Again, comparing that with the staffing level, we're getting perhaps a little bit more of a correspondence, but again, it's not a perfect correspondence, and I'm not sure that's the right thing to do anyway. Okay. So what if we look at how staff compares with arrivals, compares with numbers of people in the department, and also compares with length of stay and breaches? It's got lots of lines on this, sorry about this. Let's just try and make a little bit of sense of it. So the staffing pattern is this purple dotted line here. So that's how the staffing pattern goes. It's nothing like the arrival pattern. It's actually not really like the number of patients in the department either. It's as if they've done it, ignoring that sort of information. And the consequences of that are that these are the average lengths of stay of people over the day, and the last one, the red one, are the breaching numbers at different times of the day. So it would be nice to think what would be a really good way of balancing these things. What would a really good profile look like? Okay. So what we're starting to do is use queuing models to try and predict how much work there ought to be at different times of the day, allowing for the fact that we've got these different arrival rates, and allowing for the fact that the work goes through the system over quite a period of time, often up to 4 hours, before it hits needing to see the nurse for the last time or something like that. Okay. So the queuing models predict the work we'd like to do at different times of the day. The offered load is a phrase for it. And all I've done here is say, let's suppose that this is the sequence that someone goes through. There are other sequences as well. But if that were the sequence, they are assessed by the doctor, and that takes 40 minutes or so. They then need some tests to be taken and those to be done and arrive back, and then they can eventually see the nurse. What would these offered loads say for the staffing levels? So here we see, just graphed on the same axis, the arrival rates peaking at perhaps 11 o'clock. The staffing levels associated with these offer loads. Here we're seeing the doctors, which are before the nursing in this example. So they're not peaking at 11 o'clock, they're peaking nearer to 12 o'clock. And then the nursing workloads are peaking, perhaps another hour or so later, is the sort of thing we're getting from there. So that would be the sort of way in which we would think that staffing levels should be varied. Okay. And, for quite a few of the hospitals, we don't think they're necessarily understaffed. It's just they put the staff on at the wrong times. If you added, if you redistributed the person hours to different times of the day, we think they should be able to cope better. So this is just an example that one of the hospitals has been working at. Again, we've not finished the work, but the yellow line, for instance, is the hour-by-hour doctor staffing level in the department. And again, peaking 5 o'clock or so each day of the week. No change between Monday, Tuesday, Wednesday, Thursday, Friday. Saturdays and Sundays a little bit lower. If you work out these offered loads, what we think the staffing levels should be, then we get these orange lines. Really very different from what is happening, and we'd expect that to make quite an impact on the throughput of the department. The nurse numbers, this is just one particular type of nurse. These were nurses in the major area of work. You see the same sort of thing. The nursing level is just the blue line, which is a little bit hard to see, but basically they have 4 of those nurses available all the times, except when they drop it to 2. And again, there's quite a bit of scope for planning it better. Okay. So using that sort of method, we can try and work out what the consequences would be of this new staffing one versus the current staffing one. Okay. So using the model, we would see that if you just rearrange the staff, the mean time would drop down from just under 3 hours to 143 minutes, and the percentage getting through within 4 hours would increase from 82% to 92%. So, you know, that's good for what the model seems to be telling us. Now, with all these sort of things, you want to try and check that the model of what's happening at the moment agrees with what really is happening at the moment. Because, you know, a model isn't a perfect representation of what's going on, it's a way of representing it mathematically. And you find it's getting the average right, but in fact, somehow, at the moment, this is a year or 2 old data, they were getting 98% through within 4 hours, despite the fact the model said it should only have been 82%. And that's because the model can't go into all the detail of this business of, you're getting very close to 4 hours, I'm going to deal with you next. So it's a biased representation of what's going on, but it nevertheless is a representation. So you have to accept it's a bit biased, but then you say, but we can see it has dramatic effects in those sort of terms. Okay. For instance, if you then looked at the graph of time in the system, the blue one now is essentially what the real data said for this hospital. And again, you see it peaking at 240 minutes, 4 hours. Because the model doesn't operate this extra priority system, the model says that if you naturally allowed people to be treated in the order in which they arrived, you'd get that sort of distribution. So they clearly do need to take this dramatic effect of rushing people through, so to speak, in order to achieve the 4-hour one. If you just restaffed, you'd get much closer to achieving it without having to do any of this extra struggling to get people out on time. Okay. And you then see the consequences of it in other ways as well. How busy are the doctors at different times of day? Again, this is the full 160-hour week. So under the existing staffing levels, the doctors, for certain chunks of time, are basically busy 100%, okay, even on average. You wouldn't wish it to be 100% on average. You would wish it to be nearer to 80 or 90% on average. So under the revised system of same number of doctors, but just at different times of the day, we get this much more even utilization. Same sort of thing true for the nurses. Okay. Same sort of consequence. If you graph how long people spend in the system on average by time of day, in the as-is system, what they're doing at the moment, it's like that. If you reschedule the staff, it evens out the workload and it evens out the patient's experience. That's in terms of total time in the system. That's in terms of time to first seeing a doctor. Okay. Okay, so that's the final example I've got. Thank you very much for your interest.